Good evening to you all. I'm Robert Dijkgraaf, Director and Leon Levy Professor here at the Institute for Advanced Study. And it's a pleasure to welcome you to this Institute lecture, which actually is sponsored by and is held in conjunction with the meeting of the board of AMIAS, which is the Association of Members of the Institute for Advanced Study. It's kind of our alum organizations. And to say that the Institute is one of the few organizations that counts its researchers among its alums. And it's very important, you know, more, I think, of up to 6,000 former members are, you know, at various prestigious positions all across the world. And we are extremely proud on that legacy of the Institute, and the AMIAS organization is kind of key in capitalizing on all that engagement and goodwill. So as part of the proceedings, we always invite the most successful member ever to give a lecture. And that's today Max Tegmark, professor at the Massachusetts Institute of Technology. Just before we were chatting about what a wonderful time he had here as a member. In fact, Max was a member here from 1989 to 1990, and then again from 1997 to 2001, which was kind of a golden period of cosmology, particularly, I think, for young cosmologists. Just saying, you know, what a terrific group of scholars were arranged around that time. Matthias Aldeaga, our faculty member in cosmology, was among that. So I said, you know, I want to present Max as Exhibit A, and he said Exhibit M, to show now what, in some sense, I cannot say more, that the work that's being done here by our members, particularly our young members, is such a terrific way in which the Institute imprints and projects itself on the world of scholarship. And often that we really are a breeding ground for the next leadership in academia. And this is really true for Max in many, many different ways. He is a great scholar, extremely active in the field, published more than 200 technical papers, and he has been featured in dozens of science documentaries and popular pieces. He's also a great storyteller. I must say I was a little bit worried whether he would show up, because I remember a long time, I think I saw on your website stories about how the Tegmark family is kind of notorious of being late or wrong. And I think he was telling the story about his father, who kind of, I think, set a record by showing up exactly at the right time and the right date, only 1 year earlier or something. So, so I'm very happy to see you here. What I said is, in some sense, the most glorious day, I think, of the year at the Institute. The campus looks so wonderful. Now, Max is terrific. You know, he has, just in terms of background, got his PhD from the University of California in Berkeley in 1994. And before joining MIT in 2004, he was an assistant professor at the Institute of Pennsylvania. He received numerous awards, including a Packard Fellowship, a Cottrell Scholar Award, an NSF Career Grant. I think you were here as a Hubble Fellow, working with John McCall. His work, and that's actually the work he was working here also in his Institute days, on the SDSS, which is the large survey, the Sloan survey, digital survey of galaxies. In fact, it was, you shared the first prize for that collaboration of Science Magazine's Breakthrough of the Year in 2003. It's incredibly well-cited and influential survey. I hope we'll see something of it today. You're also a fellow of the American Physical Society. Today, I think you're telling us over a very small topic, namely how humans have always kind of repeatedly underestimated not only the size of the cosmos, but also, I think, our power of the human mind to understand that. Well, you're in particular using it mathematical equations. So in Dutch, we say bringing water to the sea. I think the English say bringing cokes to Newcastle. But in some sense, bringing this point of view to the Institute is a little bit similar to that. In fact, Max has explored his ideas in an absolutely wonderful book. I can really recommend it because it's in some sense outside the box thinking, but then on paper, Our Mathematical Universe, My Quest for the Ultimate Nature of Reality. The New York Times described it as science writing at its best dynamic, dramatic, accessible, brilliantly argued and beautifully written. It's never less than thought-provoking about the greatest mystery of existence. And at the end of the lecture, you can actually see we are partnering with our local bookstore, Labyrinth Books, so that you can acquire copies of that book. And I think you will have a brief signing, a book signing at the Common Room when we actually will have a reception after lecture. As always, there will be a Q&A with Max, but now I think I would like to, for you to join me in welcoming Max back to the Institute to give a lecture, Our Mathematical Universe.
Thank you, Rob. Thank you, Robert, for that all too kind introduction and for inviting me back here. It's such a pleasure to be back here in Princeton. I feel a wave of nostalgia, both being on the grounds and looking out here and seeing so many wonderful faces who inspired me so much in the past. I see Freeman Dyson sitting here, for example, and I've talked with many of you earlier in the afternoon. I want to start by thanking, therefore, the Institute for Advanced Study for taking a chance on me when I was just a little postdoc and giving me this great opportunity. John McCall, my mentor here, Netta, and so many others, and Robert already mentioned a bunch of the postdocs in the group I was with. As you can see, I've gotten a little older since, many of whom I've kept in touch with, had a lot of fruitful collaborations with over the years. Just to get a sense for how long it was that I was here, this little guy, Philip, who was born here, just reached an altitude of 6 feet. But that amount of time is still small compared to the age of our universe, of course. And that illustrates the main theme I want to tell you about tonight, namely underestimation. We humans have again and again underestimated not only the size of our cosmos, repeatedly discovering that everything that we thought existed was just a small part of a much grander structure, a planet, a solar system, a galaxy, a cluster of galaxies, a universe, maybe even a hierarchy of parallel universes. But we've also underestimated repeatedly the power of our human minds to understand our cosmos. And this second underestimation is less often talked about, and I want to dwell on it quite a bit in my talk and explore why is it that we've been able to figure out so much more than we thought we could, and what does that mean for humanity, for our place in the grand scheme of things. Let's begin, though, with the first underestimation, the size of things, and talk a bit about what we humans have figured out so far about our place in space during the first 13.8 billion years of our universe. So let's begin here in the Himalayas and just go for a little ride. When over 2,000 years ago, Eratosthenes in ancient Greece for the first time figured out the size of this ball that we live on, people were shocked by how vast it was. 40,000 kilometers all around. He figured this out not with a lot of clever technology, but just by clever use of his mind, looking at angles of shadows and things like this. And it didn't take much longer back in ancient Greece until people also, like Aristarchus, figured out how far away the moon was and other things in our solar system using similar ingenuity. And they realized that those things are vast, not with rocket power, but with mental power, which in turn, however, gave us the rocket power that put all these satellites into orbit that you can see here in various colors of green and blue. What I love about this animation, courtesy of the American Museum of Natural History in New York, is that everything is exactly to scale. This is not artistic license in any way. So now, for example, as the orbit of the moon starts to come into view, you don't see the moon because it's to scale. That's how vast the moon's orbit actually is, this here. And it takes 8 minutes for light to reach us from the sun, just to get a sense of scale. It takes hours for light to reach us from the outer planets in the solar system. So when you communicate with a spacecraft on the way to Pluto, you have to be very patient when you send the message. You have to wait until the signal gets there and comes back. Yet this solar system was, of course, also just something that turned out to be a tiny piece of something much grander. Raise your hand if you know anybody personally who was born before 1925. So, for these people, raise your hand if you are born before 1925. Yeah, awesome. So Freeman Dyson was born in a different universe, because back then we didn't even know that there were other galaxies. Only in 1925 did Edwin Hubble realize that this galaxy we live in is just one out of a vast number of other ones. Only then did he realize for the first time that the Andromeda Nebula, this little spiral-shaped thing, wasn't the silly little gas cloud out there between stars, but another, what they then called island universe, with hundreds of billions of stars in it. And with the Sloan Digital Sky Survey that Robert mentioned in the beginning, but they argued the Harlow-Shapley debate, right, was between some very smart person who said these are galaxies, Herschel was one of them, and another smart person who said no, it's nonsense, they're not galaxies. So we should appreciate how recently technology has really shed light on this. And the dots you see here in this structure, every little dot there now is a galaxy with hundreds of billions of stars, and they themselves, in turn, turned out to be part of even larger structures. Groups of galaxies, clusters, superclusters, enormous filamentary patterns spanning 1 billion light years in size. So it's just really remarkable how even after Hubble's breakthrough, it turned out that even the galaxies themselves were part of much bigger things. And all of these bigger structures in turn are part of this, which we affectionately call our universe, or our observable universe. And my wife, Maya, has kindly brought our universe along here for us to play with. You are also welcome to play with it if you're kind and gentle with the one universe we have here. Now, up until now, what I've said is sort of intuitive, in that the farther away we look, the more stuff we see. Nothing surprising about that. But what is the deal with this weird sphere? Why is there a big sphere at the outside here? And what's with all the yellow and green? And it's quite strange. To understand this, it's not enough to talk about our place in space. We also have to understand our place in time. Fortunately, that's quite easy to learn about, our place in time in astronomy, because, as I already mentioned, our sky is like a time machine. We see the sun 8 minutes ago. If it's clear tonight, which it looks to be, you'll see a lot of stars the way they were hundreds of years ago. So if there's somebody there looking at us, they won't see the Institute for Advanced Study. They might see the Battle of Princeton during the Revolutionary War. And if we look really far away, we can see things which happened billions of years ago. There are even some galaxies here which we see 12 billion, even going on 13 billion years ago. So by simply looking at objects at different distances from Earth, we can already learn a great deal about cosmic history, just by having it stare us in the face. So what have we learned about our cosmic history then from this? We've learned something very, very surprising. And just to help you appreciate how surprising it is, I want you for a moment to imagine that each one of you is a galaxy. And I'm looking at you with my telescope, okay? What do I see? First, I notice that you guys here are all about 100 years old. And you guys here are in your 80s and 90s, and 70s, 60s, 50s, and there are a bunch of teenagers. In that row, I see a bunch of toddlers. And way in the back, the second last row, I see just a bunch of infants in little car seats lying there. And the last row of the room is empty completely. This is pretty strange. Why this sort of strange OCD behavior? Why did you have to organize yourself by age when you sat down? Did Robert tell you to do this? It's quite strange. But that's exactly what we see when we look out into our universe. Old galaxies nearby, young galaxies farther away. Another strange thing we see is you're all blushing. You guys here in the front are just a little bit pink. But those of you in the back, I mean, positively tomato red. And further compounding my puzzlement, I see that the whole back wall of Wolfenson Hall is glowing at me with some incandescent glow of microwaves. This is what we actually see. Why? What does that teach us? Well, the sorting yourselves by age part is actually quite easy to understand, because when we look out at our galaxies, we see the galaxies nearby, they were the way they actually were pretty recently. Whereas the very far away ones, of course, we're seeing them the way they were long, long ago, when our universe hadn't had time to get particularly old. The galaxies hadn't had time to get old. That's why nearby I see you mature, well-developed, big galaxies, and far away we see these smaller ones, sort of half-baked. The empty last row of the room is this period here, the so-called dark ages of our universe, when we're looking so far back in time that no galaxies had had time to form yet. There must still be something there, the raw material out of which the galaxies later formed, namely hydrogen and helium gas mainly. And we'll come back to talk about how one can measure that. But first, what about the blushing then? Why are you blushing? If you go down to Route 1 when it's not rush hour and listen to cars, you hear them go, ew, ew, ew. They do not sound, ew, ew. Why is that? It's the Doppler effect, right? If you have something receding from you, the frequency gets lower, ew, as the car goes away. And the same works not just for sound waves, but also for light waves, which means the colors shift more towards the red. So the fact that you're all blushing, all of you galaxies, means you're all flying away from me. This is what we mean when we say our universe is expanding. And since those of you far in the back of the classroom are blushing more, you must be receding faster to figure out how far, and you're all, interestingly, also moving almost straight away from me, as if you had all been kind of here in the past. I can figure out for any one of you how long ago you were roughly here by just taking the distance and dividing by the speed. And interestingly, Edwin Hubble discovered that things that are about twice as far away are also going about twice as fast. So you get approximately 13, 14 billion years as the time of the crime for all the galaxies. So this tells us that about 14 billion years ago, something really weird happened where everything was squished together at very high density. You have to correct a little bit for accelerations and decelerations, but they almost cancel out. And you get something very strange happening about 14 billion years ago. We don't know exactly what it was. We have a fancy name for it, though. We call it our Big Bang. But even though we're still very much grappling for understanding of what happened back here, we have a very clear understanding now of what happened in the 13.8 billion years since, because we can see most of this through our telescopes. And let me finally talk about the last weird thing I threw out there. The back wall of the room is glowing at us. Why is that? Well, this black stuff, which I used to think was vacuum when I was a kid, is of course not vacuum, because the galaxies must have been pulled together out of some raw material. It's actually hydrogen gas mostly. And when everything expands, so does the gas. When the gas expands, it gets cooler. That's how your air conditioners work. Now that it's getting warm and you start to turn them on, right? So as we go farther and farther back, this gas is hotter and hotter. If you take something solid like an ice cube, you heat it up, it turns to liquid. If you heat up a liquid, it turns into what? Gas, very good. If you keep heating up a gas, what does it turn into eventually? Plasma, exactly. So electrons get torn away from the atoms, and now it's suddenly opaque. You can't see through a plasma. It's just like I'm looking into this wall here. So it looks to us like behind all these galaxies is an opaque plasma screen, except we see this in all directions we choose to peer. Like we're surrounded and can photograph the inside of a plasma ball. Who is the keeper of our universe now? Has our universe collapsed? All right, where is it? Can you throw it around? Hold it up for display. So this is actually, it looks like things are printed on the outside of the ball. We're actually photographing this. You can keep it. You can keep it for now. We're photographing it from the inside. I'll show you a little bit of a blow-up of this, okay? That's what this is. It's pictures of this plasma screen surrounding us. 13.8 billion years ago, when our universe was only 400,000 years old. And the most remarkable thing about this is, even though it was predicted theoretically by George Gamow and others in the 50s, when most people thought they were just cuckoo, this was later discovered, and we have these beautiful pictures of it taken now. The WMAP satellite, some of the core instrumentation was built here in Princeton by Lyman Page and David Wilkinson and Norm Jarosik and others, and analyzed by David Spergel and many others, together with collaborators from other places. And it's really revolutionized cosmology, having these baby pictures from when our universe was 400,000 years old. You got to ask yourself, though, you know, Lyman Page is a great guy. I really respect him as a scientist, very careful. But how can you be sure he didn't screw up? These are very difficult pictures to make. The only way you could be really sure, because the science isn't based on authority that someone is a nice guy or known to be careful, you've got to check things, is to have a completely different team with a completely different instrument doing it all over again and seeing if it agrees. And I can show you now pictures from the Planck satellite, which finally released really nice pictures of this. These are the latest ones now from a few months ago. And look how incredibly well they agree. Then, except we've gone now from 3 megapixels with the Wilkinson satellite to 50 megapixels. Sharper image, but all the big cold spots are still cold spots, all the big hot spots are big hot. So this really, really worked. A fantastic triumph. And studying these patterns in great detail is the reason we've gone from arguing about whether our universe is 10 or 20 billion years old, back when I was a postdoc here, to now arguing about whether it's 13.7 or 13.8 billion years old, which is what we do today. However, just that doesn't mean that cosmology is all over. I told you how much progress there's been by getting this sort of fantastic data, but there are huge open questions as well that remain. For example, not only do we have still very little clue as to how this started, we also have very little clue what 95% of our universe is made of, whether it's, you know, what all the dark matter and dark energy is, for example, what's going to happen in the future, if it's going to end in a big chill or a big crunch or whatnot, and a lot of loose ends in between too. So we would love to address these different questions. What do we need to do to get more information from Mother Nature about it? Well, we actually, for all of those questions, would like to simply map our universe better in 3 dimensions. So let me show you how little we've accomplished, actually, on that front. Let's peel off the edge of the ball. Don't do that with one I threw out for you to play with. But you see, the information here on these baby pictures comes mainly from this thin shell that's shown in yellow here, less than 1% of the volume. This beautiful big Sloan Digital Sky Survey I flew you around in, again, less than 1% of the volume in the middle. The vast majority of our observable universe is uncharted territory, terra incognita. We would love to map that too. How can we do that? We cannot build super-duper big telescopes and take pictures of galaxies over here because they haven't formed yet. There's nothing to take pictures of. Oops. But the good news is the hydrogen gas, which is here, which will later form galaxies, we can actually still take pictures of. And in the places where the galaxies will form, there's a little bit more hydrogen already that will gradually clump into something big and interesting. It turns out that neutral hydrogen gas gives off radio waves. They're this long, 21 centimeters. And by the time they get to us on Earth in the middle, they have been stretched by the expansion of space. So if they get here and they're 10 times longer by the time they reach us, so they're 210 centimeters, then we know how far away they came from, right? So this way we can build up 3-dimensional maps. There's a worldwide race around the world to try to do this. So far, nobody has seen this signal because it's too faint. It's so faint, it's really hard. But a lot of teams are getting closer. Let me just show you an example of an effort my group at MIT has been pushing, which we started together with Matthias Alderaga, who's here, to develop a technology for doing this much, much cheaper. It takes only 2 minutes to build a radio telescope if you run fast. This is something we've had a great amount of fun with, and this actually has worked so well, this approach, where you have no moving parts and just use cheap antennas that are mass-produced and then state-of-the-art compute power to figure out what our sky looks like in 3D, that we've now teamed up with the number of other American universities to build the world's biggest thing like this in South Africa, which should really be able to make incredible maps in 3 dimensions of our universe. So that's one very exciting front forward, where we hope to get even more clues from Mother Nature about what's really going on. We certainly need more data because we have these big mysteries that we would like to solve. Let me just comment a bit more on one of those mysteries. What happened before that? This place that we can look back to 400,000 years after a Big Bang. Why was there all this hot plasma expanding like this? Where did that come from? It feels very arbitrary to just assume it started that way for no particular reason. That sounds like magic. We don't know. There are a lot of different theories out there. There are somewhat various degrees of speculativeness in terms of their footing. The most popular one in the cosmology community is a theory called inflation. There's been a lot of talk about it recently. So let me just take a few minutes to update you a little bit on this. This theory, you've seen it all over the news because about 14 months ago, there was a press conference at Harvard saying, oh, the smoking gun of inflation has been found. Ta-da! And then, because of work by a postdoc here in Princeton, Raphael Flauger and others, the questions started to be asked, and headlines like "Bicep bites the dust" started to appear. And now it's quite clear that these initial claims were overstated. That smoking gun has not been found. So what's the deal with this exactly? What's the idea with inflation? First of all, it's by far the most audacious mathematical prediction ever made by physicists. You just say, suppose there is some kind of funny substance, it's a big if, but a funny substance that has a property that it's hard to dilute. So if you take 1 gram of it and you put it into twice the volume, the density stays about the same. So now you have 2 grams. It's a strange assumption. It sounds crazy until astronomers actually discovered that there is another thing like that called dark energy, which actually exists. But if you suspend this belief and say, suppose there is such a thing, then it follows from Einstein's equations of gravity that something remarkable will happen, called inflation. And what happens is this. You get this prediction popping out of the equations that our universe began kind of like you began. First, you were 1 cell, then 2 cells, 4, 8, 16, 32, 64. And you all know that if you double something a lot of times, you get it, pretty soon you get a lot. Okay? And if you had kept doubling at regular intervals of 1 day, like what you did, for 9 months, this would have been a very painful delivery for your mother. Because 9 months in, your mass would have exceeded that of our universe. So fortunately, when you were about the size of a tangerine, you stopped doubling. You started growing at a more leisurely rate. Okay? I didn't just make this curve up. I spent way more time than I care to admit looking at prenatal studies and growth curves in the pediatric literature to see. And shockingly, it looks exactly the same as what inflation predicts for our universe. Even the y-axis is the same. Okay, for the simplest model, when our universe is about 5 centimeters, the doubling stops. The only difference is the x-axis, where it's 1 day per doubling here, and it's about 100th of a trillionth of a trillionth of a trillionth of a second there. And if you take a small piece of this weird substance and you just keep doubling it, it's not just that you get exponentially more kilograms, but you also start getting exponentially bigger speeds, of course. The arrows show how fast things are moving. So you start with something which isn't moving much at all, and now you really have quite a bang with things flying apart very, very fast. So one of the pioneers of this idea is my colleague Alan Guth up at Princeton. And it's quite funny how the journalists, when they write about this, keep getting something very basic wrong. Notice how it says here that inflation happened in the instant after our Big Bang. That's not what inflation is actually saying. the early parts of inflation, you cannot call that a hot Big Bang, because it was neither particularly hot, nor particularly big, nor particularly bangy. It's better called a cold little swoosh. It's not so hot because it got 1,000 times hotter after inflation ended. It's not so big because it was less massive than an apple, less than a billionth the size of a proton. Not much of a bang either, because the speed got a trillion times bigger once inflation was done. So the way you should think about it instead is that this early stage, the cold little swoosh, beginnings of inflation, created a hot Big Bang. The inflation is actually a Big Bang creation mechanism. So instead of putting in by hand, oh, there was a Big Bang, you actually get to make one. That's the elegance of it. Is it correct? That's a whole other story. We don't know yet. But the cool thing is, it's predicted a whole bunch of things, which my colleague Matthias Aldariaga and I and many others here at the IS and elsewhere have spent a lot of time looking for. So far, we've tested a whole bunch of the predictions. Check, 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 check. A whole bunch of them have worked out really nicely. But there was one prediction, which has long been viewed as the Holy Grail, which would be the most convincing of all, which is this. If you look at a distant image, and, yeah, Alan Guth and Andre Linde, these two inflation pioneers, were blissfully unaware that I snuck this picture of them at this Swedish crayfish party. But if you create a ripple in the very fabric of space-time called the gravitational wave, and you fly it across a stage here, then they will, of course, look distorted, because this wave will bend the light rays, right? Similarly, if you take pictures of this plasma screen, the cosmic microwave background, those baby pictures of our universe, they will also get distorted. And the amazing thing is, inflation is such a violent thing, this very rapid doubling, that it would actually create these kind of ripples with distortions that you might actually be able to see. And they're very, very long waves, ballpark 1 billion light years long. So long that we have no other objects that are that big that would be candidates really for making them. Okay? And last year, this team had this press conference led by their PI, John Kovac at Harvard, saying, "We found the ripples." And this is a sort of ripple map, never mind the technical details of it, but there was huge excitement, headlines all around the world, and they had this curve. The details of the axes don't matter. You should just notice that here is a prediction from inflation, and here are some points which appear to lie on that curve, triggering great excitement. But then Raphael Flauger here, talking with Matthias and David Spergel and Lyman Page and others, said, wait a second, maybe this is too good to be true. And they were right. It was too good to be true. We now know that what they had actually seen was, at least in part, just dust from our own galaxy that had contaminated their measurement. So, absolutely too early to uncork any champagne bottles for inflation. But what's really remarkable about this, I think, is here we have the most audacious extrapolation ever in human history, where people take physics that they've developed in labs on Earth and so on, and they start extrapolating this back by more orders of magnitude than we've ever done before, down to 10 to the minus 36 seconds. Okay? And they realize that if this crazy, audacious extrapolation is valid, it predicts something we can look for. Okay? And people are looking for it. That's amazing. The controversy we're seeing now is not the philosophical controversy. It's a controversy about data analysis, about volts, how to interpret them, right? And the best of all is that this is going to actually not be something which is going to linger forever as an unresolved question. There's a lot to look forward to. Already in this year, the BICEP team that announced this are taking pictures of the sky at another frequency so they can see if it has the color of dust or the color of the baby universe. There are also a number of other teams competing, which are going to get super high quality maps in the next few years. And my hunch is that if there is actually a period of inflation of anything like the simplest form, then one of these teams will actually see this. And if inflation is wrong, at least the simpler kinds, they won't see something. So the fact that we can have a serious scientific controversy, serious scientific discussion about something that feels so almost hubristic to even think about is a fantastic triumph again of the power of the human mind to explore our cosmos. Now that brings me to the next topic, the second kind of underestimation I promised to discuss. So far, we've talked about how we've kept underestimating the size of things and kept discovering more and more and more and understanding things better and better and better. But why is that really? Sometimes we get so used to something that we stop marveling at it. I think that's dangerous. Why is it? Why have we kept understanding more and more? If I look back at the history of science and ask myself, what are the most useful ideas ever that have really propelled science forward? There are two ideas that really tower over all the others. The first idea is make experiments. In other words, go out and measure a bunch of numbers. It's turned out to be incredibly useful, not just sit and contemplate our belly buttons, but really go out and measure all these numbers. Empiricism, the Renaissance really drove that home, and we've had incredible science ever since. But there's also a second idea, which isn't talked about quite as much, which is that when we do get all these numbers that we've measured, we should try to make mathematical models for them. We should look for mathematical patterns in these numbers, regularities. That has been incredibly successful, to the point that many scientists have viewed it as rather mysterious. Pythagoras, already over 2,000 years ago, said that numbers rule our universe. Galileo, 400 years ago, was so wowed by this, he said that nature is a grand book written in the language of mathematics. But where is this math he's talking about? I mean, let's look around the room. Do you see any math anywhere? I mean, if you look out in the sky, I don't see any numbers there. I see a number here, 3, but that's maybe kind of underwhelming because I wrote it myself. But if you look at the full quote of Galileo, you see here, he says that this book, its characters are triangles, circles, and other geometric figures, without which it's humanly impossible to understand a single word of it. So for him, when he talks about mathematics, he's not just talking about a bag of tricks for manipulating numbers. You know, my mom thinks of math as a sadistic form of torture invented by school teachers to ruin our self-esteem, right? But Galileo thinks of geometry as mathematics also. And to all my mathematician colleagues here at the Institute and elsewhere, of course, they don't think of math as just numbers. If you go walk into the office of one of the mathematicians here and take a random paper off her desk or his desk, you won't even find a lot of numbers in it, except the page numbers, or maybe an exponent in something. So he's talking about geometry, patterns also as mathematics. And then all of a sudden it starts to make more sense what he's talking about, because yes, we have found a lot of patterns, mathematical patterns in nature. Every time we throw something in the gravitational field, it always makes the same shape. What's this shape? It's a parabola. It obeys a very, very simple equation, y equals x squared. When we look at stuff moving around in the sky, Johannes Kepler realized, again, it's always the same kind of shape. We call it what? An ellipse. That's right. Again, it obeys this very simple equation. And then if you look at it a bit more closely, you realize that actually what we're taught in high school as a parabola is actually just a small piece of an ellipse. So it's all ellipses. And so that's pretty remarkable. All this very complex motion turned out to be all the same shape. And let me ask you a little quiz question. Which tool was it that triggered the discovery of these three things? The planet Neptune, the radio wave, and the Higgs boson. Which tool was it? Don't be shy. There'll be a small pop quiz after the lecture, so you might as well guess now and get the right. Mathematics. That's correct. If you want to be a real stickler, you can say it was a pencil, because they were all predicted using a pencil. For example, the planet Neptune, right? We had the planet Uranus was discovered by using a telescope, coincidentally. Boom, oh, there's a new planet. But then we had Urbain Le Verrier sitting in Paris, wondering why Uranus wasn't obeying the equations of Newton in its motion. And he calculated and calculated and calculated with his pencil. And then he wrote a letter to this astronomer Gall in Berlin and said, point your telescope to such and such a place in the sky, and I predict that you will there find a new planet. I don't know what Gall thought when he opened this letter, but he might have thought that this Frenchman was like cuckoo for Cocoa Puffs, but he was obviously just so consumed with curiosity, he had to look. And boom, there was Neptune, predicted through mathematics. And then, just decades later, James Clerk Maxwell, I'm teaching a course about Maxwell's equations for the undergrads at MIT this spring. He was just messing around with everything known about magnetism and electricity and realized there was something wrong with one of the equations. He fixed it. Then he solved these equations with his pencil, and he realized that, oh my goodness, this means I can build a certain device that can send information at the speed of light through empty space. And raise your hand if you have a cell phone in your pocket. Predicted, again, with mathematics. And just decades later, Hertz first built this, and it's, of course, revolutionized science and technology. Even more recently, Peter Higgs and others sat down again with a pencil and took the most advanced mathematical description of nature at the time, the Standard Model of particle physics, and calculated and predicted very audaciously that if we humans get together, build the most complicated scientific instrument ever built in Geneva, and we use it to smash particles together near the speed of light in a certain way, we will there predict this new particle, the Higgs boson. You know how that went? We built it, and they got a free trip to Stockholm to visit my hometown. And it's quite remarkable, this power that math has. So we can summarize so much complexity with just a few simple brush strokes and these equations. Nature has given us these wonderful clues. So we didn't just do experiments, but we looked at the numbers, we found these patterns in them. Some people are so impressed by these patterns, these equations, they even have them engraved on their tombstone. I took this picture when I visited Erwin Schrödinger's grave. And it's not just equations either. This is a table you'll find in my book from a paper I wrote with Frank Wilczek, Morton Reith, and Athene Aguirre, where we point out that every single pure dimensionless number ever measured in physics can be in principle calculated from this list of 32 numbers only, using equations. It's pretty crazy. You can take a book. I found the book up in the Princeton Library here, which had almost 100,000 numbers. It's a very old book with spectroscopy data. It's talking about exactly all the wavelengths that come out of different kind of atoms. They can all be calculated from these numbers. Amazing simplicity there, hidden in nature. Eugene Wigner, another one of my great heroes, was a professor at Princeton University for many, many years. He was so wound by this that he wrote this famous essay in the 60s saying that this is really a mystery, this enormous usefulness of mathematics, the unreasonable effectiveness of mathematics in natural sciences, something really bordering on the mysterious, and there's no rational explanation for it. So in the book, Our Mathematical Universe, I explore the full spectrum of views that people have on what to make of this. And I had many wonderful discussions, for example, with Freeman Dyson here while I was a postdoc here at the Institute about this. I explore the view that maybe this doesn't really mean anything. Maybe we humans invent mathematics, and maybe this reflects something about us humans, or whether we decide to coin names for the things we understand and ignore the rest. And then explore other sides of the spectrum too. I also had a lot of fun talking with Ed Witten when I was here, who is much more of a Platonist, who feels that he doesn't invent mathematical structures but discovers them, and that there is that math is really out there in some way, and he's hoping to ultimately find mathematics which provides either a very accurate approximation to reality or actually a perfect description of reality even. And then there's the most extreme possibility on the other end of the spectrum, which I also explore. And that's my own favorite, which is that this really means something very profound, that our nature actually, that the reason we keep finding all these mathematical patterns in nature is because nature actually is mathematical. That our universe isn't just described by math, but that it is math in the sense that our physical reality is a mathematical structure. And in plain English, what I'm saying is that this hypothesis is that our world doesn't just have some mathematical properties, but that it has only mathematical properties. Wait a second. That sounds really nuts. our physical world has only mathematical properties? Huh? I mean, just to emphasize how silly this sounds, let me introduce you to our friend Mr. Hoggles. He lives in our backyard. In fact, he probably thinks we live in his backyard. And look at him. What properties does Mr. Hoggles have? Maybe cuteness, fluffiness, herbivousness, a penchant for digging big holes in our lawn. Those don't sound like mathematical properties, do they? But yet, when I look at him with my physicist eyes, I see a blob of quarks and electrons arranged in a certain pattern. What properties does an electron have? An electron has the property -1, 1/2, 1, and so on. Physicists have made up nerdy names for these properties of the electron here. We call them things like electric charge, spin, lepton number. The electron doesn't care what we call it. The properties are just numbers. They're mathematical properties. And as far as we can tell, the only difference actually between an electron and an up quark and an electron neutrino is what numbers its properties are. As far as we can tell, none of the elementary particles that make up everything in Wolfenson Hall and elsewhere in the cosmos have any properties except mathematical properties. The positions of them are also, of course, mathematical things you can describe with numbers. So if everything in space actually has only mathematical properties, what about space itself? What properties does space have? 3 is a property that space has. That's the largest number of fingers I can hold perpendicular to one another, right? Again, we have a geeky word for this. We call it the dimensionality of space. Space doesn't care what we call it. The property is 3. It's a mathematical property. Einstein, when he worked here, talked a lot about general relativity that he had developed, which says that space also has these other properties called curvature and topology, which, as all our mathematician friends can tell us, are also purely mathematical properties. So if both space itself and all the stuff in space have only mathematical properties, then it starts to seem a little bit less insane than maybe our world really is completely mathematical. So what would that mean if it were true? Well, to me, this would actually be very good news, because if we look towards the future, I already argued that the successes we've had in the past in understanding our world better have come from finding all these mathematical clues that nature has kindly provided us with, right? So if this hypothesis is wrong, that it's all mathematical, that means that sooner or later we're going to run out of clues. We still won't understand our world fully, but there's going to be a roadblock. There's no more mathematical patterns to be defined. That's it. End of the road for physics. But if this hypothesis is correct, then there is no roadblock. And our ultimate ability to understand the world is only going to be limited by our own imagination. And I think that will be absolutely wonderful. How can we tell which way it's going to be? Well, ultimately, the way you can tell is to keep looking at the things that we still can't describe by math and see if they can also be described by math. Right? That's been tried very extensively since Galileo and others started raving about the mathematicalness 400 years ago, right? Think about it. In Galileo's time, what was it that really could be described by math that wowed him so much? It was just a tiny fraction of all aspects of reality, mainly things to do with motion. If Galileo took an apple and threw it, he could calculate the shape would be a parabola, but he had no idea why the apple was red and why it was soft enough that you could squish it with your hands, whereas he could not do that with a rock, and the rock was not red. That seemed non-mathematical to him. So people started studying those seemingly non-mathematical things. And then Maxwell came along and realized, oh, there's the Maxwell equations that describes all properties of light and colors. So it isn't non-mathematical after all. Then Schrödinger came up with the Schrödinger equation of quantum mechanics, which not only lets you calculate all the properties of matter, namely which substances are hard and which are soft and so on, but also the colors of light that they're going to emit. You can calculate from the Schrödinger equation actually why a rock certain rock looks gray and why a certain kind of Granny Smith apple is going to look green and so on. So what is it that's, it's very interesting to look today at what is it that's left in our physical world that we still have no clue how to describe with mathematics. Studying those things seems to be the natural way to tell the difference between whether it's all math or not. Well, consciousness is a great example, right? This has largely been left to philosophers by physicists because it seemed so hopeless to ever learn anything about it, much like it seemed hopeless to Newton to figure out why an apple was red or green. There was all this speculation from thousands of years, but no data, really. That's also beginning to change now. People used to think it was hopeless because you only have access to your conscious mind, your subjective experience, yourself. Nobody else does. So how can you do any science with it? But that's not true anymore. I can put you in a magnetoencephalography scanner up at MIT and just measure the magnetic field in 306 places around your head with a superconductive magnet. Don't worry, it doesn't hurt. It doesn't even touch you. And I can tell you to think about, say, one out of 25 different objects. And I'll be able to tell you with 90% accuracy always which one you're thinking of, just from your magnetic field. And the technology for doing this sort of brain reading is getting better and better. And that means maybe even this is gradually opening up now to scientific study. If you want to know, suppose you put yourself in this scanner and you look at a computer screen, and every time you think about an apple, a green apple, a picture of a green apple comes up. And then you think of something else, and that comes up. Then what you can do is a really cool experiment that hasn't really been done yet, which is you can ask how much of the information processing in my brain am I actually consciously aware of? There's a lot of stuff going on there and being computed that you're not aware of at all right now, like your pulse regulation and stuff like this. In fact, most of what your brain is doing, you're not aware of. And then you can say, well, okay, if you look at the specific subset of all that computing that you are aware of, what is it? What's the special property of that information processing versus all the other? You can look at it from outside, you can look at it from inside, you can compare, and maybe you'll find that there is some new eureka moment to be had, that there's some additional principle that when the information processing satisfies that, then there's an experience there, and otherwise it's not. Who knows? We don't know one way or the other whether math will ultimately be able to describe all aspects of the world or not. But I'm an optimist, both because I'm generally a happy camper, and also because I think it's a much more practical approach to life to be optimistic. And let me close by just explaining what I mean by that. There is absolutely no better way to fail on any endeavor in life than to convince yourself from the get-go that it's impossible, and therefore never try. Right? If you think about it, you've all had some friend at some point you were trying to encourage them to actually try the thing rather than just convince themselves they couldn't do it, right? So I think a very healthy attitude for us scientists is to take this working hypothesis. Suppose it's possible for us to describe all these things with math, then let's try our very best. Okay, if we fail, that's going to teach us something very interesting. But if we never try, we're not going to learn anything one way or the other. So in summary, to conclude, and summarize everything I have said, I'm going to go back to the beginning and just say that it's really, really remarkable to me how we've underestimated things, we humans, both the vast size of our cosmos and the ability we humans have to actually understand it. And I think we live in an incredibly exciting age now where the understanding the people before us have gained has given us this technology, which gives us even more information about the world, which we can try to use to understand things even better. And it's gotten to the point that this understanding has gotten so amazing that we can even start using it to develop technology to actually start to make a bit of a dent in our universe and actually help life flourish, hopefully even better, even more so than at the present time. And I think there's absolutely nothing in the laws of physics saying that any of the problems that afflict the human condition right now can't be solved. And the main danger is really just if we tell ourselves, oh, you know, it's impossible, we can't do it. So let's make a difference. Thank you.